of small modular reactors together with my other speakers who are professionals and ambassadors of the Russian nuclear education ambassadors. I would also like to give a shout out to Alexandria University and the RNEA organization. If everything can be done in the big manner and can actually operate, why can't we also do it in the small manners and actually operate? Today, we'll be looking at beyond. What are we looking at beyond? We are looking at beyond the big nuclear reactors. We are looking at beyond the small nuclear reactors and how it can be seen, the generation 4 reactors. To begin, I would like to welcome Hagar Hussein, who is a professional in the nuclear field, but also a student at the Moscow National Research Nuclear University. Hagar Hussein will be giving us a lecture today on Generation 4 reactors and systems. Hagar Hussein, please, the floor is yours.
Hello, everyone. My name is Hagar. Today, I would like to present with you about interesting topic. Right now, we can start. Hello, my name is Hagar. I'm a second year master student at the National Research Nuclear University, MIFI. Today, I would like to talk about general overview of generation number 4 nuclear systems. First of all, we have to understand what is the fourth generation of this nuclear system.
Your presentation isn't moving.
1 minute. What about now?
Sorry, please. It's still not moving. And could you please put your presentation into the presentation view mode?
Mm-hmm. And now?
It is still not there. While you're experiencing some technical issues.
1 minute.
Okay. While there seems to be some technical issues, I would like to ask Mrs. Hagar Hussein to please resolve the issue while we move on to our next speaker. But we'll get back to Mrs. Hagar Hussein. Is it working now?
Yes. Okay.
Yes, we are looking at the general overview of generation 4 reactors.
Okay, let's start. First of all, what is the fourth generation number 4? We can take a look about the first generation, which already started since 1950. And after that, we take a look also about the second generation, which is chemical power reactors, like Kondo. And the third generation, which is like EPR and EPWR. And after that, we are going to generation number 3 plus, RPMR and IREC. And after that, we are going to the last generation, which we already have today, and we already interesting to know more information about, which is the fourth generation, which have high economy and minimal waste and also professional resistance. Definitely, we are going to take a look about this one because we are looking for 4 key goals. First of all, it is sustainability, which is good. Start with us about the main goal, which we already have all as a nuclear engineering, which is closed fuel cycle. And after that, safety and reliability and economics and professional resistance. This kind of reactors, we already are exciting to understand and start the operation with this kind of reactors in 2030. Right now, we have 6 technology of these reactors. Sodium fast reactor and lead fast reactor and very high temperature reactor and gas cooled fast reactor and also the cold reactor and molten salt cold reactors. The difference here between them, the first one, it's VHTR, which is high temp. This kind of reactor, which is helium coolant, have like a temperature from 900 to 1000 Celsius hydro production. And the second one, sodium closed fast, which is using liquid sodium already temperature inside. It will be from 500 to 550. And this one is already reach us for the best target, which is closed fuel cycle. We are going to GFR, which is same idea like VHR, and it's helium coolant also, but with more temperature, which is 850 Celsius, and per the reactors. The last one, which is SCWR, aspirated water, and this one have temperature between 510 until 625 Celsius, and also high efficiency. Right now, we can take a look about the experts in Russia. In Russia, they start this journey, and we can say there is the first country who have a nuclear reactor which works with fast neutrons. Can take example for PN 600 reactors, which already start operation since 1980. And this the capacity in this reactor, which is 600 megawatt to 506 megawatt. They experience it more than 45 years, and also they have a target for this lifetime target for this reactor, which will be more than 60 years. And it will be the longest reactor operation, which is have life operation for the fast reactors. After that, they already have to develop this kind of this reactor. After the good target, which they already did, they start the PN 800, and this one already started the operation since 260 to 2060, and capacity it will be improved. It will be it was 2100 megawatt to 789, and it's 100% mixed fuel. And why Russia leads this kind of reactors, we can understand that Russia have more than 390 reactors year over reactors experience, and the only country who will start working with the fast reactors. Also, they are proving the molten sodium cold technology. And right here, we can also see the Prest OD300, which is the first lead cold Gen 4 reactor. And this is technically led by Cold and have minus 500 Celsius operation temp, and also capacity, which is more 300 megawatt. Have key navigations, which is interesting design, natural safety, and closed fuel cycle. This one is located already in Siberia and Tomsk region. The timeline, it's already started to build since 2021, and it will be starting to operated 2029 or 2028. And this is already under constructions. And this one is the next generation, which already Russia looking for. It will be PN 1200, the next generation of the sodium fast reactors. And this is the most powerful neutron reactor planet. But we can say why? Because according to specific information, this one have a thermal power which is more than 1,200 megawatt, and also it's giving electric power 500 megawatt, and also design life it will be more than 60 years, and also revolution interval extended. And also it's sharing with other kind of reactors like PN 800 use mix fuel. right here we are already making like a comparing between this kind of reactor PN 1200 and also PN 800. The timeline for this project, it will be since 2025. Construction will be start maybe at 2027, and we are looking for start the operation in 2034. Um, like here we can see the most interesting project which already Russia have, academic Lomonosov, and this is the only operating floating MPP. It's already located in Antarctica. The power of this Lomonosov Academica is interesting, and also they have a major of achievement which is 1 billion kilo generated, and this is a peace refloating in 2023. Which is have power than 60% of Western Chukov and replaced coal-fired planet, and also supported by Paminsky meaning. It's already located in Chukotka region. It's the far east in Russia, like I said before, Antarctica. Right here, we can understand the future version which Russia are looking for the fourth generation roadmap, which is they already have. Russia already interested to have more than new nuclear units, more than 34 planned by 2042. Also, they want to share more nuclear. They would like to share electric generation by 80% to 23.5%, and the target of this year it can be so soon it will be 2042. And right here we can take a look about the timeline of the new project which already Russia have and for the future until from 26 to 2042, which is Prest OD 300, RITM export, and PN 1200, and also PR 1200 flat. And it will be operated in Uzbekistan, Middle East, and Kyrgyzstan and Africa. Thank you for your attention. I would like to answer all your questions.
Thank you very much, Mrs. Haga Hussein, for a powerful presentation on Generation 4 and system reactors. May I also state to the audience that while the presentations are going on, you could jot down questions, set your questions down, and after all presentations have been made, we will visit the chat sections and ask the questions to our speakers to answer them. Now, there's a saying in life that if you want to go far, you go together as a couple, which is why atoms most probably make all things together. And if you want to go fast, you go alone. Looking at that from the university studying electrical engineering, Mr. Falkenberg is going to actually deliver a powerful presentation on fast neutron reactors, and he's going to explain to us the fast neutron reactors and the elements which compose of it. Mr. Falkenberg, the stage is yours, please.
Thank you, Emmanuel, for the introduction, but I'd just like to clarify that I'm not doing electrical engineering. I'm doing high energy physics, as you can also see on the title page of my presentation. And thanks to Haga for giving us some overview of Generation 4 International Forum that have really identified some of the technologies that we are going to talk about today as fundamental in addressing some of the issues that we have in the nuclear field. And one of those technologies that is seemingly very interesting and has proven so far that is worth our attention is what we call the fast neutron reactors. So I'll delve into this, just some minor details of how fast neutron reactors operate, and also several philosophies that have been adopted by 3 countries that we'll be able to tackle in a few minutes. So this is the outline of our discussion today. I'll first try to give the clear distinction between several circuit configurations that we encounter in pressurized water reactors. and also, of course, for the fast neutron reactors. And it's really crucial for us to take it from that direction because mainly the pressurized water reactors happen to be the source of the spent nuclear fuel that we utilize in our fast neutron reactors. And of course, we'll also try to talk about the physics, just the basic physics of fast neutron reactors, a little bit about the neutron spectrum and interaction cross-sections, and then we'll delve into the reasons why they tend to be very crucial for us in our nuclear field. And in addition to that, we'll also talk about the several design philosophies adopted by Russia, India, and of course, France, and so forth. So these are the typical circuit configuration that you have. For the pressurized water reactor, this is figure one. You can see this is basically a two-loop configuration. There is a primary circuit that is constituting the fissile zone, of course, and the coolant in the primary circuit. And of course, there is a second circuit entailing the steam generator and so forth. Then for the fast neutron reactors, we usually have mainly two configurations, but of course there are several other configurations involved too. So for these configurations, we have what we call a piped configuration. You can also just call it a loop configuration, where we have especially the pre-loop. So there is a first loop in the circuit that constitutes a radioactive sodium, and that is a primary circuit, of course. Then there is an intermediate circuit between the primary circuit and then the steam generator, which contains what we call intermediate sodium. So in the first circuit, the radioactive sodium, the sodium in the primary circuit is exposed to radioactive radiation. That is why we are referring to it as radioactive in that case. But in the second circuit, you can see we have sodium that is isolated from exposure to radioactive materials in the fissile zone. And that is really crucial for us because safety is also a priority in this case. And we have to ensure that at no point we have the leakage of a sodium that is exposed to radioactive material to the environment. And the major distinction that I would also like to point out is that for fast neutron reactors, we do not really need to raise the temperature of the primary circuit, the pressure within the primary circuit, because sodium has a substantially higher boiling point. So it will really maintain that state that we require it to maintain while the cooling process proceeds. So you don't need to raise the pressure within the core. The boiling point of sodium is about 880 degrees Celsius, and the operational temperature, the average operational temperatures for fast neutron reactors are somewhere between 500 to roughly 550 degrees Celsius. So you see there's a huge margin, and in normal operations, there is no need for pressurizing the primary circuit in any way, the way we do with the pressurized water reactor. So, and then the second most common circuit that you also have for fast neutron reactors, you can also see is what we call an integral circuit configuration, which is also a pool type configuration where the primary circuit and the fissile zone and of course the primary pump, you can see they are all immersed in a single containment. And this is also crucial. One reason could be that we do not want to have several exchange surfaces, that because they should be efficient heat transportation from the fissile zone all the way to the steam generator. So that is an integral configuration. And of course, there are other configurations too, but these are most common in fast neutron reactors. And then we'll talk slightly about the physics involved. So this is what's called the neutron spectrum and interaction cross-sections. It is very crucial to point out that in fast neutron reactors, we have to ensure that the moderation process does not really proceed normally like we have in thermal reactors. Yeah, because we are operating the fast neutron spectrum. So we have to ensure that the materials that we are using within the fissile zone do not facilitate the moderation of the neutron from the fast neutron spectrum to the thermal neutron spectrum. Because we typically know, you can also see from this attached figure here, the neutrons are typically born as fast neutrons. But if we are working in the thermal spectrum, that is with reactors like the PWRs, then you have to ensure that there is moderation process so that the neutron goes to the thermal uh, regime. So in the thermal regime, there's preferential interaction with certain materials. Of course, you see that in a thermal regime, the fission co-section, for instance, for uranium-235 is high. Plutonium-239 is high, but the fusion co-sections are also going down as we are approaching the first regime. And again, it's important to point out again from this figure that the fusion co-section of materials like uranium-238 start manifesting in the first regime. So basically means we can use these materials uh, to be adopted as fuel in the first regime. So you'll see how that happens in a couple of few minutes. So other cross sections that are also crucial to talk about are what called the capture cross section. So in the capture cross section, there is a preferential interaction by absorption method. But when absorption, it's called absorption without fission, where the target material like uranium 238 basically captures the neutron and then it gets to an excited state. So the material simply gets excited and could further subsequently be subjected to what we call nuclear transmutation, which is a very crucial concept for us when we are doing what we call breeding process, which we want really to manifest in fast reactors. So that is really dictated by this probabilistic interaction processes within the reactor core. So we have to check this capture fission cross-section ratios, the fission capture cross-section ratios. So if it's a higher capture to fission, capture fission cross-section ratio, then that means then it's a possibility of a plutonium breeding process where the uranium-238 captures a neutron and then it's subjected to the breeding process and so forth. And then this is now one of the reasons again why we would prefer to adopt fast neutron reactors. This is the management of the spent nuclear fuel, like we said before, that what you have in a pressurized water reactors is a spent nuclear fuel, and of course, in most cases, the nuclear material adopted is underutilized. And so we have to investigate within the spectrum, the Newton spectrum, the particular regime that is preferential for these processes. So in the spent nuclear fuel, we have what's called a long-lived radiotoxicity materials. So these are materials like minor actinides. You can see them listed on the screen. And usually for the disposal of utilized materials, usually we do the disposal by geological methods. But then an alternative route for doing that is what called nuclear transmutation. And we can do nuclear transmutation in the fast neutron spectrum. So what happens is that we take the spent nuclear fuel, and then we have to subject it to reprocessing in order to separate this minor actinides that you have. Then these minor actinides have to be subjected to fabrication in pellets, more or less the same as what we do with the typical fuels that we use, for instance, in pressurized water reactors. And then we do the irradiation process in the fast neutron spectrum. But then that irradiation process, we repeat the process until we are satisfied that the resulting materials are either short-lived radioactive materials or they're stable materials. So that is really the essence of doing that repetition. Then it means we have to identify the preferential interaction mechanism, because if this material, the target material, interacts with a neutron, then it could interact by capture or fission. But you can see, for instance, from this attached figure here, if you pick a americium 241, it can interact with a neutron by neutron capture and then to americium 242, and then it's subjected to beta decay. You get this. But now you see the end result is really not preferential because you're basically increasing the atomic masses. So this is worse. So this is the worst of them. So we have to ensure that the interaction process that is happening is one that would give us isotopes that are short-lived. Yeah, so that can happen in the first spectrum. So in the first neutron spectrum, the preferential interaction mechanism of minor actinides with the neutron is basically by fission process, which will give us isotopes that are short-lived or isotopes that are basically considered, materials that are considered stable nuclides. But if we are doing, if the interaction process happens with the through nuclear through capture process, then instead of destruction, we simply end up with a scenario where isotopes that are worse than the ones we had initially manifest. So yeah, that is the significance of nuclear transmutation process. We are basically having some fertile material that absorbs a first neutron and then it's subjected to subsequent transformation into other fissile materials that are utilized as fuel in fast neutron reactors. And then this is now some typical design approach that has been adopted for the fast neutron reactors, the European design. This is a MOX core, or the mixed oxide core that you can see here. I've attached a subassembly for the fuel constituting several. You can see here we have the material. The material mixture is also attached in the code snippet. So, but what I wanted to point out here are the materials that have been adopted. For instance, for the hexagonal materials, the hexagonal wrapper material that you can see adopted in our sub-assemblies here. These are what we refer to as the EMH, EM10, sorry, the EM10 steel. So the EM10 steel has some special mixture of chromium content and molybdenum. It's about 9% chromium content and 1% molybdenum content. And of course, other materials that we also are very keen on are the materials that are adopted for the cladding of our fuel, like the ODS steel or oxide dispersed strengthened steel, which has very superior high temperature and strength. And then it also has its radiation hard. So that because this is a very intense environment, and we have to ensure that the materials can have a long-lasting structural integrity. So we have to be very careful with the materials that are adopted. So the code snippet attached here can help you really understand the mixtures in our materials. And then, of course, this is now the core design. For our reactor, the figure 6 is an axial view. You can see the stratification for the axial reflectors at your own time when you get this presentation, and you can also see the fissile zone and so forth. But what I wanted really to emphasize on is the radial view of the MOX core here, in this case, where there's a central subassembly constituting a reflector material, and then there's a special sub-assemblies that contain what you call the control shutdown devices and the diverse shutdown devices. So there's a first string immediately you can see this is brown. The first string constituting sub-assemblies with control shutdown devices. Then the ring between the inner fuel zone and the outer fuel zone that at the boundary also contains what you call the control shutdown devices. Then between these two rings, we have the diverse shutdown devices that are utilized. Those are what you call the control protection system that are utilized in conditions of a normal operation of the reactor core, and also when there has to be some facilitation of an emergency shutdown of our reactor. So you can see from the code snippet the materials adopted for our reactor core here. One thing I just wanted to point out is a manifestation of americium 241 here. It's very strange, but it serves a very crucial purpose, and its proportion is also very low, as you can see from the mixture. It's basically added in order to take into account the beta decay of plutonium 241, which is also available in the fuel mixture. So at your own time, you can go through the code snippet. And lastly, on the on the European design, this is the control and protection system. The left figure with the blue with the left trigger, you can see this is what you now call the control shutdown devices, the ones we utilize in situations of normal operation of the reactor core. and the right is what's called the diverse shutdown devices. The difference between these two is basically the content of absorber material in this case, which is boron 10. So on the left, the boron 10 percentage in the mixture is roughly about 20% from natural boron, but on the right we have the enrichment levels have been increased up to 90%. So we want a situation where if there's an emergency shutdown, then we simply uh, adopt these diverse shutdown devices, and they should be able to absorb the neutrons instantly in order to tame the fusioning process, so the chain reaction that is happening within our reactor core. So yes, that is a control and protection system adopted in the European design for their first reactor. And this is a Russian design philosophy adopted, basically what you call a build and operate learn approach, where they are basically using they are learning. So for instance, you assume some worst case scenario and then you take into account the design just to tame it. So this is a very crucial approach. And so far, they've demonstrated several concepts using the first reactors they have in their series, what called the BN series, which had also talked about, so BN 350, the BN 800, and of course there is a one that will be commercial, the BN 1200, which is currently under development. But this is a first reactor concepts that have been adopted by Russia so far. And lastly, this is also an interesting one. This is an Indian approach, what's called the prototype fast breeder reactor. It's really a special one, in its kind, because it's a multi-stage approach, because we know that the spent nuclear fuel material comes from pressurized water reactors, for instance. So therefore, why don't we have an integration of this where the output from the first stage is the input in the next stage and subsequently to other stages until we have something that we are satisfied with as far as utilization of nuclear materials are concerned. So for the first stage, for instance, you can see here, this is operating on the thermal spectrum, uranium-235 interacting with the neutron fusion products and some neutrons we have there. But then I just wanted to point out the main output from this stage that we are really mainly interested in for the next stage is plutonium-239. And then in the next stage is where we now have the prototype fast breeder reactor, where the energy production happens. So plutonium-239 interacting with the first neutron, the fusion process, like fusion products and neutrons and so forth. But then another special thing about this reactor is the adoption now of the thorium. As we all know, India has the largest thorium reserves in the world. So they have a thorium blanket this stage for the thorium reactors. So the thorium blankets can also facilitate these interaction processes that we have one for fast reactor. So you see the thorium-232 neutron capture to thorium-233, and all the way at the ultimate end, we have uranium-233. And then similarly in the same thorium reactor and uranium-233 interacting with the neutron, the fusion process, and then several neutrons and the fusion products. But again, lastly, what I would really like to point out is this management of the minor actinides, which also happens here. As you can see, americium reacting with the first neutron, the fusion process, and this is the destruction that you want. But there's also a potential interaction, which is basically the capture process that we don't really want, because ultimately, if a capture process happens, we end up with worse material than what we had in the previous case. So this is an approach that is adopted by India. You can have a look at it, but it's really an interesting one too. But these are basically three different design approaches that are ultimately looking forward to a common goal. That is, how do we ensure that there is a proper utilization of nuclear materials that we are adopting in our reactors. So the first reactors are giving us some promising advancements that we really need in order to handle used nuclear fuel that we have so far. So that is all I had for you today. There wasn't enough time, but you can always find me from RNEA in case you have any other clarifications that you need. But if you have questions, I'll also be interested to answer them today. Thank you very much for your attention.
Thank you very much, Mr. Falkenberg. And now, as we have looked at how Generation 4 can help, Generation 4 systems help, and we have also seen that going fast is also not bad with fast neutron reactors, which was a lecture delivered by Mr. Falkenberg Cyril. We are now going to look at the smart way to do things. If something can be big and move, but you can also make it small and move, which makes it portable. Hence, we're going to move into our next lecture from being small with the small modular reactors. This lecture will be delivered today by Mr. Godwin Ojori, who is studying at St. Peter's the Great Polytechnic University. Mr. Godwin Ojori, please, the floor is yours. Thank you.
Hello, everyone. Is my presentation visible?
Yes, yes, it
Yeah.
is, Mr. Godwin.
Okay. So, good evening, everyone. Thank you, Emmanuel, for the warm introduction. My name is Godwin, studying at Peter the Great, St. Petersburg Polytechnic University. And today I'll be talking about small modular reactors, SMR. We've been hearing the buzzword around and around and around. And today we'll finally get a basic understanding of what they are and where we can use them. In today's webinar, I'll be talking about what SMRs are, and we'll be comparing them with conventional nuclear power plants. We'll also be looking at some of the key benefits, the pros of the adoption of SMR. We'll also look at how SMR are applied around the world. We'll look at some of the safety concerns, because when it comes to nuclear energy, safety is key. And we'll look at some of the projects, exciting projects we have all around the world. And now, without much further ado, I'd like us to dive right into what we are doing today. And that is SMR. What exactly are they? Just as the name implies, SMR, small modular reactors. The small talks about the size and the power output, whilst the M talks about the modularity, how they are produced and how they are deployed. And reactors, well, that hasn't changed so much. They still use nuclear fission to generate heat, which in turn is used for electrical energy generation. So now let's go into more details on what we mean by small. So in comparison with traditional nuclear reactors, SMR produces about less than 300 megawatt electric per module, while the traditional nuclear reactors produces northward of 1,000 megawatt electric. And by contrast, we can see a big divide between them. I mean, the size is by no means random. It has a purpose. It is meant to take nuclear energy to areas where large nuclear reactors would be impractical. And we can see that typically they vary from 1/3 to 1/10 the size of traditional nuclear reactors. If we go to the next section, which is the modularity part, we'll look at the size comparison of the microreactors, the modular reactors, and the traditional reactors, of course. Microreactors are, as the name implies, micro. They are quite small, and they typically produce from 1 to 20 megawatt electric, and they are small enough to be transported in trucks. Small modular reactors, on the other hand, like I've said earlier, produces about below 300 megawatt electric per module, and usually transported by rail and water view. And traditional reactors, they are quite large, taking up land mass of hundreds and hundreds of acres of land, producing about 1,000 plus and above megawatts of electric. And that is enough to power about 1 million homes. New SMRs, on the other hand, can power about 300,000 homes. So we can see the size disparity of these reactors. And if we go to modularity in the sense that the design and the construction approach, the way we approach the design of these reactors, we can think of them like Lego blocks. So we build them in bits and pieces, and then they are transported to the deployment sites where they are assembled and they begin functioning. We can also see a comparison of SMRs and traditional NPPs, where the traditional NPPs, they're built on site, taking about 5 to 10 years for construction, with delays and being exposed to the elements. But whereas the SMRs are built in factories in a controlled environment where they're automated. And if you understand economics, anything that can be automated, the price of it drops drastically. And that is one of the benefits of having SMR technology. Now I'll move forward to talk about the reactors. Well, like I said earlier, the reactor still functions more or less in the basics the same, converting through nuclear fission, generating heat, which in turn generates electricity. There are a couple of reactor technology available in the world today. One of them, which is my favorite, is the marine-based water-cooled reactors. And an example of that is the prestigious Academical Lomonosov that started running in 2019 in the city of Pevek. We also have, like my colleague Cyril spoke about, the fast neutron reactors, and they operate at very, very high extreme temperature, around 1,000, if I'm not wrong, around 1,600 degrees Celsius. We also have the micro reactors, like I spoke about, from 1 to 20 megawatt hour electric. We have the molten salt, and these are still R&D. A company in South Korea, Hyundai, they are working on this at the moment. We have the high temperature gas-cooled reactors. These has been operational since 2023 in China, the HTR series. And we have, of course, the land-based water-cooled reactors. So these are some of the examples of the reactor technology we have at the moment and the ones that are still being developed. Now I'd like to talk about the benefits of SMR. We've spoken about a little about what they are and how they function. Now let's talk about the benefits. When it comes to technological advancement, economics plays a key role. If it's not economically viable, it doesn't work. Right, and that is why the first key benefit we'll be talking about is economics and time. Compared to the traditional nuclear power plants, SMR, they are deployed basically from 3 to 5 years. And if we look at the traditional and conventional nuclear power plants, they take from 5 years to 10 years to be developed. And what that tells us is that the longer it takes for a technology to be deployed, the more you spend, right? And SMR cuts down the cost of building and deployment down significantly. Another benefit I love a lot is flexibility and scalability. And what does this mean? It means that, for example, you deploy an SMR reactor in a rural area, a rural community. And let's say there's a boom in the economy and then energy demand grows. What do you do if you have an SMR? You just add another module. Unlike the conventional nuclear power plants, it's quite technical if you want to do that, to add and increase the power output. But SMR makes that quite easy and straightforward. The next of which is the fuel requirement. What this talks about is that the conventional nuclear power plants require fuel replacement every 1 to 2 years. It varies, but for SMR technology, it takes from 3 years to 7 years. And for some microreactors, they are predicting it might take somewhere around 25 to 30 years before you need refueling. And lastly, I'll be talking about the versatility in applications. Conventional nuclear power plants are built with one goal in mind: electricity generation. Whereas nuclear SMR, which is the small modular reactors, are built with versatility in mind. So we are not building them just for electricity production. They have a plethora of other functions they have in society. And an example of this we can see is the Finland LDR-50 that was built mainly for district heating. We also have other cases of SMRs being used for hydrogen production, for ESMR, where we want low carbon hydrogen. And these studies have been taking place in France, in Germany, and also in Switzerland. And lastly, like I said earlier, we have the marine propulsion, which is being done by the Hyundai South Korean company. They're trying to develop molten salt coolant pumps for SMR. I'd like to delve into versatility just a bit in the next slide. We can see here the versatility of application. This is just a visual representation of what I was saying earlier on, SMR being used to provide backup electricity generation for intermittency of solar and wind. And we can also see them being used as a main source of electricity for data centers. I'll talk a little bit on this later on. Like big companies like Google, Meta, and Amazon, they invest in billions and billions of dollars to advance the nuclear energy, which is in this case the SMR, because of the boom in AI and data centers. We can also see SMR being used for low temperature heating, which is the district heating of homes, and also being used for hydrogen production in different plants. We can also see them being used for high heat in high temperature process heating. And these are just some of the ways the SMR can be implemented and can be used in the society we have today. Next, when we talk about nuclear energy in general, as it's a source of energy that is quite vital to humanity in terms of application and the benefits it poses, it will be quite injustice to downplay the danger it also poses. And that is why we'll talk about the safety that SMR presents. So we'll look at the safety features and we'll compare the safety features of the traditional NPPs with the SMR technology. Traditional and conventional NPPs mainly rely on active safety. And what does active safety mean? It means the auxiliary system depends on electricity. And what that implies is that in case of blackouts, the system is quite vulnerable, like we saw in the case of Fukushima. And also it requires human intervention, which is operators. So you need the operators to do whatever it is they do to prevent a meltdown. But SMR, they rely on passive safety. Passive safety means they rely on natural phenomenon like gravity, natural circulation, and convention for self-regulation of the system. And that means that even in blackouts, these systems work. And there are 4 key components that ensures this safety, this passive safety feature. And one of them is the condensate heat exchanger. And what this does is that it condenses steam back into water, and it transfers steam from to the cooling pool, which helps in removing the heat decay. Another of which we have is the emergency cooling tank, which is kind of like a heat sink that is built to absorb heat for days and days on end. We also have the core markup tanks, which is a water tank placed directly above the core. In case of emergency, the valves open and gravity does its work. It pushes the water down, and this is quite automatic. And lastly, we have the isolation condensers, and this uses natural circulation. So hot steam goes up, cold water goes down, and then you have a continuous loop. So you don't need a pump. Gravity does all the work for you. Next, we're going to look at some of the interesting and exciting SMR projects we have in the world currently, one of which is my favorite, the Academical Lomonosov, which is the world's first floating nuclear power plant that was commissioned in 2019 in the city of Pevek that supplies heating to the Arctic communities. And we also have the HTR PM in China that was commissioned in 2023. It uses tri-structural isotopes as the fuel. We also have in different regions of the world, one of which is in February of 2026, Poland commissioned a 24 reactor from BWRX-30 series, and this is one of the most commitments of any European countries. We have also from Canada, from Romania, and what this shows us is that SMR is gaining momentum. SMR is moving, and it would be unwise, as we can also see from all the popular companies like Amazon and Meta and Google, what they are doing currently. They're investing billions and billions and billions of dollars into these projects because they have done their research and they can tell that SMR is the future of nuclear energy. And I would like to conclude now by saying that I don't believe SMR would replace conventional nuclear power plants. That's not what I'm saying. I'm saying that SMR gives us the ability to take nuclear energy to places where large nuclear reactors will be impractical, and also for applications that large nuclear reactors wouldn't necessarily provide us. From data centers to the remote Arctic locations like the academical Lomonosov, from industrial heating to hydrogen production, SMR is becoming the new standard of nuclear energy. I leave you with these few words. If you have any question, I'll be willing to take them. Thank you for your attention. Thank you.
Thank you very much, Mr. Godwin. Thank you very, very much Mr. Godwin, for the powerful presentations. And we're going to move on to the question section now, after receiving three powerful lectures from three great ambassadors. Moving over to the questions, I can see your interesting questions in the chat, and I will attack straight ahead. So, Mrs. Haga Hussein, there's a question for you. And the question goes, how do generation 4 systems and small modular reactors address the limitations of traditional nuclear power? And how is Russia currently leading this global transition? Mrs. Haga?
Hello again. This is an interesting question. And this question already have two parts. First of all, we can understand that SMRs and fourth generation systems, they have a mission. They are solving a traditional problems which we already have with the old generation of nuclears reactors. As we can see in SMR's reactors, they are power plants, they are smaller and cheaper. Most of the countries, they can't build MPP. They didn't have enough money, they didn't have enough area to build this kind of reactors. And we can see like in global way, they already start to be interested more about opening a market for SMRs reactors. Like in Brazil, in Indonesia, these countries already invested a lot of money of this kind of market for using SMRs for the future. Also about the generation number 4 of the reactors, we can just understand this kind of reactors, they are not helping us to get more electricity. No, this kind of reactors, they are solving a big and a huge problem which we already face today, which is the fuel waste, which we already have. This kind of reactor can be used for recycle the fuel waste because they are burned the nuclear waste as fuel, which is already solve a big problem for the pollution, which make nuclear more green and sustainable systems. And also it can continue with us for thousands for years, and you can use the same fuel which already it wasted before after recycle for the new reactors. It's mean you didn't have to go and look around for uranium. No, you already can make your own fuel by using the fuel which you already you recycled before. The second part from this question, why Russia lead this generation? We can just make sure about one truth. Other countries, they already start all of this new. They start to design, they start to solve this problem. Maybe it's more theoretical, but Russia have the expert of this. They have more experience. They have already this PN 600, which already operated and working more than 45 years. That's why this operating technology which they have, it can be using to help people and other countries to start also this project with Russia. About the operating technology, we can see that Lomonosov academic, it's not that easy. Imagine you have a floating nuclear power plant, which can give electricity in every area in this planet. And also this kind of reactors, the fast reactors, the recycles of fuels, all of this make Russia at the first place of using this kind of technology. As we see before, while other countries are still testing the designs, Russia already building and share the experiment, this advanced and SMRs to the other nation. I hope you like this answer, and if you have another question, I will be so happy to answer.
Thank you very much, Mrs. Haga Hussein. While you spoke about the Russian systems, there's a question here which I think would be of interest to you. And it states, is Russia currently developing any micro reactors or planning for micro reactors development in the future? Ms. Hussein,
Yeah, again, please. I didn't listen your question.
Ms. Haga.
Yeah. Can you ask the question again? Please, Emmanuel, can you repeat the question?
Can you hear me now?
I can
Can
hear
you
right now.
hear me, Mrs. Haga?
Yeah. Okay, any other question?
If I can take over, I have a question, Hagar. The
Please.
question is about like what factors are prompting the advancement of nuclear reactors? Why are we moving from Gen 1 to Gen 2 to Gen 3, Gen 3 plus? Like, what is the factor that is associated to why there is this advancement?
Okay, we can negotiate about that. The difference here about the technology. We can understand the first generation of the reactor, they are just care about the safety and make electricity. At the second generation, it's more capacity. At the third generation, it's more sustainable, more green, and start to take a look about the problem which we already have from the first and second generation in the reactors, like fuel, and they start to looking for solving these problems. Fourth generation, it's already solving most of like 90% of this problem. In the first and second generation, we can just take the waste fuel, and put it in the ground, and like we try to deal with it, but we can't recycle it. But if we are comparing between this kind of generations and also the fourth generation, we can find out that we can recycle this kind of fuel. We can use it again. Like imagine you are already working in a closed cycle. You have like the fuel waste, and you recycle it again, and you start to do it again. You didn't have to look around for uranium. You didn't have to start to make a new fuel, because you already have your fuel which you already recycle. This also is good for the environment, because as we understand, we are not just looking for energy. We are looking for energy. We are looking for clean energy. For SMRs, as I said before, and small reactors, most of the countries didn't have the ability to build MPP. We are not say that we are not building more MPP. No, this is a different way. But imagine in your country you didn't have the enough places or enough money, or you can't wait like for 15 years to build MPP. You need energy. In this case, you can use SMRs, and I already mentioned that we can take example for countries already interested in this kind of reactors, Brazil and Indonesia, and SMRs right now is not just using for energy, as we say. Before, you can't sell an MPP. Just Rosatom and in Russia, they take the decision to share the experiment and help other nations to have their own energy and build with them MPP. But in another countries, if you need energy, you can't open a market to sell SMRs. But right now, we have this ability.
So if I get it correctly, it all depends on the advancement in technology, right? We learn from mistakes. So the mistakes we find in Gen 1, we try to solve them in Gen 2. The mistakes we find in Gen 2, we try to solve them in Gen 3, correct?
Yeah, because in these times they didn't have like enough experiment to understand what is the problem. Like imagine you are like 90-50, you are getting this whole amount of electricity, and after that what is the problem which we are looking to solve? The fuel. Okay, we will put it in the ground, we will try to deal with it. But after that, you can find out by making experiment and working with this technology more and more, you can find a new way to solve this problem and make it helpful for you. It's not a problem anymore. It's a plus. It's not a minus.
Yeah, that's good. Okay, so the next question goes to Falkenberg Zero. We have a question from Sumojit. The question is, can engineers inherent chemical reactivity of FRS coolants, specifically sodium, to a level of reliability and safety that justifies their high construction cost and proliferation risk?
Mm-hmm. Thank you for the question. There is a concept that you've mentioned there on chemical reactivity that you didn't really have enough time to talk about. But yeah, from a technical and operational point of view, we can basically say that this chemical reactivity issue has been solved. Yeah, because you remember I talked about, for instance, I talked about in the design, I talked about the double wall. I didn't really mention that it's called a double wall, but then if you saw from the the circuits, the typical circuit configurations that were in the slide. There was a circuit that has an intermediate loop. So when there's an intermediate loop, we are basically isolating the primary loop from the steam generator, so that we are eliminating any potential manifestation of radioactive sodium in areas that it should not really manifest in, because we don't really want a situation where the radioactive material leaks into the environment. So that is one technical aspect in which we address that issue. And of course, we also have what we refer to as the inert atmospheres, because we know very well that there could be an explosion in the event there is manifestation of sodium in the vicinity of air, for instance. So we just fill the portions within our designs that could potentially be filled with air. We fill them with some inert material like sodium. I mean, what do you call this? Nitrogen, or sometimes with argon. Yeah, so this eliminates that air environment, so that we have that safety aspect where there is no potential explosion when sodium gets exposed. And then we also have, I think now if we go to an operational history standpoint, because Russia has been operating the BN series for quite some time. And I think it was BN 600 that sometime way back they had a sodium leak, but then they handled it safely. So far they have over 40 years of experience operating this particular reactor, and there has not been any potential issues with it so far. I mean, that has posed any challenge to the people, because basically when we are working with nuclear reactors, we have to ensure, number one, that we prevent, I mean, we protect the environment, and of course, avoid exposing the inhabitants to radioactive material. They managed to do this so far, and the BN series is basically operating with molten sodium as a reactor. But then on the cost aspect, I would say not really. This is where the answer becomes no, because we have solved the chemical puzzle for the sodium. We know quite a lot about it, but then it's still really very expensive. Like a case example of the redundant mechanisms that you have to take, they are very complex in the design, so they are expensive, but in the long run, they are safe. Yes. So if that, I mean, if that is the case, then obviously the economic aspect is still an issue that needs to be addressed.
Okay, that was wonderful. Thank you. And we also have a question here from Ahmed Soliman. Sorry if I didn't pronounce your name correctly. You have a question for Godwin, our passive safety system, and identifying features of SMR. So meaning, if I am designing an SMR, is it a must to implement a passive safety system? Well, the short answer to this is no. There is no strict requirement or a legal mandate that is compelling you to do that for SMR. However, passive safety has become more or less like a dominant design philosophy we have in the world today, right? And that is why most producers of SMR technology are reliant on that, right? So, but it's not a must that you must do that. However, it is in the world we are today, it's highly popularized, right? So that is going to be the answer I'll be giving you for that. The second question you have is that to Falkenberg, could you explain in exercise 5, in your slide 5, spent nuclear fuel management? So how do we optimize the process of fuel cycle integration so that most of the left spent fuel are short-lived nuclides, or at least most suitable for geological disposal? What is the process of optimization?
I think for optimization of this process, we simply have to adopt, I think there's this concept we call extended burnup. So we basically increase the fuel residence time in the reactor. So if we increase the fuel residence time, we expect to achieve higher burnup. And if that happens, then the benefit of that is that there's consumption of the fissile material, and then there's reduction of waste per unit energy. So it's basically from that aspect. But then this also has certain limitations, of course. We are extending the fuel residency time, so we've got to deal with issues like cladding integrity and so forth, higher enrichment requirements and forth. But again, I think there are other aspects that are really advanced. The advanced technologies within the fast reactors, where we now have the closed fuel cycle with multiple recycling. Because you remember in my slide, I indicated a section where we basically have to take this spent nuclear fuel material and subject it to reprocessing. So when we reprocess, we are basically interested in isolating several other products from the fuel, but mainly capturing the minor actinides, because these are the long-lived, we have long-lived minor actinides that I mentioned, like americium, neptunium, and curium. So we have to isolate them from this used spent nuclear fuel material, then subjected to a fabrication, just like we do with fuel, and then irradiation. So there is continuous irradiation with neutrons within that environment, of course, within a very specific spectrum. So fast neutrons, just to ensure that we reduce, they become less toxic, what you call short-lived, because we have long-lived radiotoxicity. So perhaps you can make them short-lived radiotoxicity or maybe stable. So it's simply a repetitive process. So we'll do the radiation until you're satisfied that these materials are basically suitable for either geological disposal or basically uh, with very short-lived, less radiotoxic to the environment. Yeah, so that is one of the advanced techniques adopted so far.
Yeah, thank you very much. We've spoken a lot. We've said we've given a couple of interesting information, and I believe everyone here has learned one or two things about the advancements in nuclear energy. And so if you found this webinar quite useful, and if you've probably gotten a very good information from this webinar, do well to scan the QR code below. You can follow us on our social media platform, Facebook, on Instagram, on VK, and on YouTube. We post contents like this. We post challenge, and it's a fun place to be, trust me. So scan, like, follow our content. So thank you everyone for your presence today. We really value and respect them. We are happy to see you here, and till the next time, goodbye guys. Thank you very much for coming. Thank you very much.